Welcome everyone. My name is Dr. Mudita Juneja. I am from the Department of Electronics and Communication Engineering, Tirthankar Mahavir University, and this is my video lecture in Network Analysis and Synthesis. Today, we will be discussing the two types of network functions. First is the driving point function and the second is the transfer function. So let us start and first know what are network functions. So every network is designed to produce a particular output when the input is applied. The network performance is judged by studying its output for the applied input. Thus, once the network is designed, the effect of network parameters remains same on the input to produce the output. The effect of network parameters is mathematically expressed in the S domain, which is the Laplace domain, which is called the network function. It is also sometimes referred to as the system function or the transfer function of the network. It is the characteristics of the network, and once known for any type of applied input, the output can be predicted. So in short, we can say that these network functions define a system. They give the characteristics, the features of the network. So when this sort of a network is given, which is defined in the S domain as GS, the network is defined as GS. The input or the excitation is given as capital ES, and the response or the output in the output side is given as RS. Then the network function is mathematically defined as the ratio of Laplace transform of output, which is the response of the network, to the Laplace transform of the input, which is the excitation applied to the network, under the assumption. Now this assumption is very important whenever you are defining any sort of a network function, and the assumption is that all the initial conditions are zero. Like initial conditions we have when there's a capacitor, there's an inductor, and we have the initial conditions for 0 minus or 0 plus or anything of the sort. So the initial conditions have to be kept 0, then only these network functions can be defined. So mathematically the network function is denoted by HS, GS or TS as the case may be, and it is given as the ratio of output, that is the response, RS upon excitation or the input ES. Right? As you can see, all the three entities are in the Laplace domain. Now there are some of the properties of the network functions, some of which we've already understood, but we will state it here also. First is that it is a mathematical model of the network. That is, it gives the mathematical representation of the network, explaining the operation which the network performs on the input to produce the output. Second is, it is the characteristics of the network and is unique for a given set of input-output. Third is, the network functions are independent of the magnitude and nature of the input. Any input will be applied, but it will be evaluated on a network function which will already be given, and that will remain the same in spite of whatever the input may be. Only the output will change correspondingly. The network function will remain the same for a given network. For any applied input, the output can be predicted from the network function. This is very clear, as network function is a ratio of the output by input. So if the network function is given, the input has been applied, the output will be calculated as a product of the network function input. Now the initial conditions lose importance while obtaining the network function, as we have already seen that the initial conditions are set to 0 to evaluate the network function. Now the next property is that the time domain differential equations of the input output can be derived from this network function easily, and thus we can say that the network function gives a full description of the dynamic characteristics of the network. That is, if the network function is given, then we can totally define the characteristics of that particular network. Next is the excitation and the response of the network may be currents or voltages. Hence the network function may be an impedance function, admittance, voltage ratio, or the current ratio transfer function. This we will discuss in the upcoming slides. Now there are two types of the network functions. First comes the driving point function and next the transfer functions. Now the driving point functions are defined when the two quantities involved, the output and the input, or the response and the excitation, are of the same port. And the transfer function is defined when the two quantities, the two variables, the response and the excitation, are from two different ports. So in case of a one port network, a single port network, we can only define driving point functions, and in that case we cannot define the transfer functions. Whereas in a two port network, both the driving point functions as well as transfer functions can be defined. Now let us see through the definition of these. A ratio of voltage or current at a port to the voltage or current at the same port is called a driving point function. Now a ratio of voltage or current at one port to the voltage or current at the other port. These two quantities, the numerator and denominator, are from two different ports. Then this is called a transfer function. The various types of driving point function are driving point impedance function when it is voltage by current of the form, and admittance when it is of the form current by voltage. Next, the transfer functions can be of four types. Voltage transfer functions when both the numerator and denominator are voltages. Current transfer when both the numerator and denominator are currents from the two different ports. Impedance functions, transfer impedance functions, when the numerator is voltage of some port and the denominator is current of the other port. Similarly, the admittance, transfer admittance function. So let us see what are driving point functions. For a given network, the ratio of Laplace transform of the source voltage and source current is called the driving point function. If it is a ratio of source voltage to source current, it is called the driving point impedance function and is denoted as ZS. While if it is a ratio of source current to source voltage, that is vice versa, then it is called the driving point admittance function and it is denoted by YS. The driving point function is nothing but the impedance of the network as viewed through the input or the output terminals. As YS is reciprocal of ZS, these functions are generally termed as immittance function. Immittance is a combination of impedance and admittance. So these both driving point functions YS and ZS can be combined, called as the immittance function. Now the condition that the initial conditions are assumed 0 holds good in this case as well. Now the driving point function will be defined as this: PS upon QS. These are the Laplace transforms, and PS is the numerator polynomial, QS is the denominator polynomial. Now what are the necessary conditions for driving point functions? Now if there is a common factor between the numerator and the denominator polynomial, they are cancelled, and then we define certain necessary conditions for driving point functions. These are: the coefficients of the numerator polynomial, which is PS, defined as PS, and the denominator polynomial must be real and positive. That is, the coefficients cannot be imaginary or they cannot be negative. If the poles and zeros of that network function are imaginary, then such poles and zeros must exist in conjugate. the real part of the poles and zeros must be negative or 0. Now this is for the stability condition. And if the real part is 0, then the pole or 0 must be a simple pole and not multiple poles. There should not be any missing term between the highest and lowest degrees in the polynomials unless all the even or all the odd terms are missing. The degree of the polynomial in numerator and denominator should differ by either 0 or 1. The terms of lowest degree in PS and QS may differ in degree at most by 1. So these are few of the necessary conditions for driving point functions. Next we come to the term transfer functions. Now as we already discussed, it is also the ratio of certain network parameters, but those two variables or the parameters will be from different ports, right? These functions may be voltage ratio, current ratio, transfer impedance or transfer admittance of the network. They are also determined under the same assumption that all initial conditions are 0. And the next is that there are no dependent current or voltage source in the network. Now the transfer function is also a ratio of two polynomials as we defined earlier for the driving point functions in S, which is the Laplace factor. Now in a similar way, you can see the necessary conditions for transfer functions are: the coefficients of the two numerator and denominator polynomials must be real and positive. This was also there in the earlier case. Next is the complex and imaginary poles must be in conjugate. The real part of the poles must be negative or 0, and if it is 0, the poles must be simple, including the origin. There should not be any missing term between the highest and lowest degree unless all the even or odd terms are missing. The polynomial, that is the numerator polynomial, may have negative terms or even some missing terms between the highest and the lowest degree. This is a bit different from that we already read in the driving point functions. Degree of polynomial may be as small as 0, independent of the degree of the denominator polynomial. Now we can see the mathematical representation of this transfer function as well as the driving point functions. Here for a one-port network, you can see there are two terminals in the one-port network. The voltage is V1 and the current, as you can see, is I1. So the driving point functions defined here are: first is ZS. This is the driving point impedance function. As you can see, there is only one port, so that will be Vs upon Is. These are the voltages and currents shown here. Similarly, the admittance function will be Is upon Vs of the same port. Now for this two-port network as given, the input voltage is V1 and the input current is I1. The output voltage is V2 and the current is I2. So these are few of the standard notations for the transfer functions defined. First is the transfer impedance Z12, where the numerator is the voltage of the first port, port 1, and the current is taken from the second port. So these are two quantities from different ports. That's why this is a transfer function. Similarly, the transfer impedance Z21, which is V2 upon I1, transfer admittance Y12, transfer admittance Y21, the voltage ratio transfer function, which is a ratio of the two voltages from the two ports, V2 upon V1. This is defined as G. Now alpha is the current ratio transfer function, which is I2 upon I1. Now in this case, if we want to find the driving point function from the input side, driving point function, then the two entities in the numerator and the denominator will be from the same port. So the driving point impedance of port 1 will be V1 upon I1 the driving point admittance of port 1 will be I1 upon V1. Similarly, the driving impedance of port 2 will be V2 upon I2, and the driving point admittance of port 2 will be I2 upon V2 respectively. Now let us see to some of the numerical questions which have been solved here. As you can see, this is a two-port network given. First port is defined as 1, 1 dash. The voltage is V1, current is I1. The normal general notation is given. Similarly, the voltage and current at port 2 are V2 and I2. So first we need to evaluate Z11. This Z11 will be the, as you can see, 1 and 1. So both the numerator and the denominator entities, quantities are from the same port 1. So this is a driving point impedance function. Impedance because this is Z. Y is used in case of admittance and Z is used for impedance. So this is a driving point function. Next we need to find Z21. As you can see, 2, 1. So both the entities are from different ports. So this is a transfer function where 2, that is the numerator, will be from port 2 and the denominator will be from port 1. This is also an impedance function. And third, we need to find the voltage transfer ratio G12. As you can see, G12, so the numerator will be from port 1 and the denominator from port 2. So let us evaluate this now. As you can see that IL, the current through the inductor, would be, if this at this point the voltage is V2, then that would be V2 upon this impedance 2S for the inductor. So IL will be V2 upon 2S. Then the voltage across the capacitor would be V2 plus 2 times of IL. As you can see, this is an open port and voltage is given at this port. So the current which flows through this inductor will also flow through this resistor. So the total voltage across the capacitor will be voltage across this 2 ohm resistor and then the voltage across this inductor. So VC, the capacitor voltage, would be V2S into S plus 1 upon S. Then the current would be upon impedance, that is V2S into this function. So it will simplify as S plus 1 into V2S. Similarly, we can find the value of I1, which is the total current, IC plus IL. Now V1, that is the input port voltage, will be VCS plus the current flowing through this I1S. Then this total voltage will be evaluated. So what we need to find is Z11S, which is V1 upon I1. This can be calculated from all the previous calculations. This is calculated as this. As you can see, the numerator polynomial is 2s square plus 4s plus 3 and the denominator polynomial is 2s square plus 2s plus 1. Similarly, the transfer impedance function Z21S will be V2 upon I1. This is also an impedance function. This will be calculated as 2 upon 2s square plus 2s plus 1. Similarly, the voltage transfer function G12S is calculated as V1 upon V2, which is calculated as 2s square plus 4s plus 3 upon 2s. Now again consider this ladder network given. As you can see, an inductor and a resistor. Then the parallel branches have capacitors, all of the same values. So first we need to find the open circuit driving point impedance Z11. This will be of this general form. You all must be aware of this general form of the impedance. So here in this series branch, the total impedance Z1 will be S plus 1. Y2, the admittance in this parallel branch, will be 1 upon S. That will come to S. As 1 upon S is the impedance, so the admittance will be 1 upon this quantity, which is S. Similarly, Z3S, Y4, Z5 all will be the same repetitive way. So now Z11 will be evaluated just by substituting those values in this manner, and we have evaluated the driving point impedance at port 1 as a ratio of these two polynomials, where the numerator polynomial is S6 plus 3S5 plus 8S raised to the power 4 plus 11S cube plus 11S square plus 6S plus 1, and the denominator is S raised to the power 5 plus 2S raised to the power 4 plus 5S cube plus 4S square plus 3S. So this is the driving point impedance of port 1. So thank you everyone for watching this video lecture. I hope it will be useful for you and you will understand this topic better. Thank you all.